This question is relatively easy, but doing it well requires some really important problem-solving techniques. After you solve the problem and get a feel for what I'm talking about, I'll walk you through what goes on in my mind as I work through the problem. And there is a way of solving problems that's reliable and not so dependent on luck, and I want to show you what that ideal process looks like. And I can't emphasize this enough, but if you want to get anything out of this exercise, you have to solve the problem on your own first. So hit pause now and give it a shot. Any programming language is fine. So I assume that you've taken a shot at this. Here's what I would do. So the first thing is I want to rephrase the question in my own words. And this is an important part of turning this jumble of words into a crisp idea that I've fully internalized. So as I'm reading this, I see that we want to write a function. It takes a string. That string may or may not contain zeros and ones. And then finally, it returns the number of zeros within 2 steps of a 1. So what I'm doing is I'm breaking this apart into pieces that I can analyze one at a time. So function doesn't matter, it's just an organizational thing. String is important in the sense that we're dealing with a sequence of characters. And then this part really just describes a string, but we'll decide whether this is important later once we understand the question a little bit more. And then here we can see that this is the heart of the matter. We need to return the number of zeros. So we get to return a count, and that count has to represent everything that meets this condition. So we have this condition, and this is definitely important, and this is where I'm going to focus my attention. Now let's go back and think about whether this is actually important. Like, does this say anything that's not already said in the rest of the question? So if there are no zeros, then we just won't return anything, which is implied here. And then if there are no ones, then none of the zeros that we might have would meet our condition. So there's nothing that's being said here that's not already in this last portion that we're already focused on. So this is just kind of irrelevant extra information. It's not essential. So I'm just going to delete it, basically. It's just a distraction. This last portion talks about zeros in the aggregate. But if we're going to solve the question with a computer, we need to rephrase it from the perspective of an individual zero. And that gives us something like this. And this is something a computer can solve. Now to get this back to the aggregate, though, we need to add a modification, which is for each zero in the input. And this gives us a way to repeatedly ask this question across the entire set of zeros. So now these things are logically equivalent. I'm realizing now, too, that we basically are getting a strategy for free. This is something that might work. So let's go ahead and fill out the rest of the requirements. We need to have a count that starts at 0. Whenever we get to a 0 that fulfills this condition, then we want to increase that count by 1. And then finally, we return that count at the end. When a plausible strategy emerges, there's the instinct to get excited and just run with it. But I've been wrong enough times to know that this should be the time to think really hard about whether this will actually work. And rather than do this with specific inputs, which is what most people do, I like to think about correctness as abstractly as possible, because when I focus on inputs too much, it's easy to miss important aspects of the problem completely. So let's revisit the text and consider what needs to be true about a correct solution. So one, we had to return a numeric count, and then of course that count must represent all the zeros that meet our condition. More specifically, if we dig into that, a 0 that passes the condition should be counted once, and then a 0 that doesn't pass the condition should not be counted. And if we manage to do all those things, then we should get a correct answer. So these are the requirements for a correct solution. So does our approach meet all these requirements? yes, it returns a numeric count. It counts a valid 0 once. Well, it inspects each 0 once and then checks if it's valid. So number 2 is yes. And then 3, that's also yes, because we only increment the count when we have a 0 that passes our condition. So we meet all of these guarantees, no problem. This approach is correct. A lot of people like to jump to code as soon as possible, but usually it's a bad idea because it forces you to think about minute details before you have the big picture. And in this case, I want to spend a little bit more time figuring out what exactly happens when we stumble upon a 0. And a good way to do that is to draw a picture and visualize that. So let's imagine we're going through the string character by character, and then we hit a 0 at this point. What does it mean exactly to be within 2 steps of a 1? Well, 2 steps to the left, and then 2 steps to the right. If we branch out left, and then we branch out right, and ask ourselves, is there a 1 in any of these 4 slots? Then we'll meet our condition. So this is the picture I see, and we're going to be doing this each time we hit a 0 in our input. So as a sanity check, I want to run through our example inputs and just make sure that our strategy makes sense. So our first one is 1000. And here's where it's really useful to have this visualization technique because we don't need any code to test our strategy on inputs. So we're going to do something at each 0, and then we're just going to branch out, look 2 spots to the left and right. Here we have a 1 spot to the left, so we count that. In the next 0, we have a 1 right here, so we count that. And then in the last 0, there are no 1s in any of these slots, so we don't count that, and we return 2. And then with the other input, 0, 0, 0, 1, we're going to examine these 3 zeros. We have no 1s in these slots, so we don't count the first 0. We have a 1 right here, so we count the second 0. And then here we have a 1 right here, so we count the third 0. And we also return 2, just like we're supposed to. As we're tracing through these examples, I notice there's a potentially tempting new approach, which I'm representing with this picture. So it's almost the same as the one above, but it's subtly different. Instead of examining every 0 and branching out, we will examine every 1 and branch out. And the reason that this is so tempting is more obvious when we trace through the example. So when we take the perspective of the 1 instead of the 0, we examine 1 element in each of these examples, the only one, and then we just branch out 2 spots to the left and then 2 spots to the right, very similar to the way we did it before. And then if we see any zeros, we count them. So this 0 is 1 spot over, this 0 is 2 spots over, and then we return 2. This 0 is 1 spot over, this 0 is 2 spots over, so we count those, and then we also return 2. And so superficially, this seems to be correct, and superficially, it also seems to be simpler and less work. I think it's also really tempting because if you immediately jump to the example inputs and look at the first one, it starts with a 1, and so your mind might wander to thinking about this approach rather than the one we did before, which came from really analyzing the problem statement and rephrasing it in our own words. So if you jump to the example inputs, you'll be even more tempted, I think, because the first example starts with a 1, and then even later, if you come up with the initial approach we did with the 0 perspective, you still might be tempted because this picture looks pretty good. Before we get carried away with this new idea, we need to ask the hard question, does this even work? And here's where the analysis we did before is really useful. We know that a correct solution has to meet these 3 requirements. So does this new idea do that? So number 1, yes, Number 3, also yes. And number 1's more obviously true. Number 3 is true because if we stop at every 1 and we look 2 spots over, then those zeros are going to be guaranteed to be within 2 spots of a 1. So we're not going to count any invalid zeros. But number 2 is problematic. You just can't tell right away whether we're going to count a specific valid zero one time. In the old idea, we examined each zero exactly once, but there's no such guarantee that that's happening. We do have the guarantee that we're going to look at each one once, because that's where we're going to stop. We're going to stop at all the ones, but I don't know about the zeros. And so there's a risk that this might not be correct. And just on that reasoning, I probably wouldn't go down this path if I was in a time-constrained environment. I would point out this risk factor where we're not sure about 2, and we would need to do more work to figure it out. Here's how I would definitively answer the question about whether this new idea fulfills this requirement. So I'd keep it at the conceptual level with the drawings. And first, let's think about what we're actually doing here. So if we stop at every 1 and then branch out left and then branch out to the right, what we're looking for is any valid zeros because we want to find those and include them. And we want to, at this point, have some guarantee or assurance that we're only going to count a valid zero one time. So let's think about this. Let's imagine the input right here. We're at a 1, we stopped, and let's say that we have a 0 right here. In order for this 0 to be counted, it needs to have 1 branch above it, and if it has only 1 branch above it, then it'll be counted only 1 time. But what if there are multiple branches above it? In that case, in the current conception of this approach, we would count this 0 twice. So let's imagine there's a 1 right here. We're going to count this 0 once from the perspective of this one. And then when we get to this one, the second one, we're going to count this 0 again. So currently, this approach is broken. It will not work. It will require some mechanism to avoid this double counting issue. Since this approach requires some unknown mechanism in order to work, we can dismiss this approach as definitively worse. We already have a strategy that works fine and is obviously correct and is simpler. So there's no reason to go down this road. There is educational benefit to doing that though. When you have these ideas and then you see a roadblock, trying to figure out a way around that has a lot of educational value. And you have to think creatively in order to address this issue. So I'll give you one hint. There are different ways you can solve this. But one thing that you can see from this problem is that we don't want to look to the left when we've already examined these indices before. And so if we look at the same input where we have a 1 here, a 0, a 1, let's say another 0 here, and we're going to examine the 1s. At this point, we have examined everything up to this line. So we can somehow record that. And then when we examine a 1 again, we can know, hey, don't look back past this line to the left, only look this way. So that could be one way to address it. And there are other ways too. I encourage you to think about that as practice. Since all of the hard thinking is already done, implementation should be more or less a typing exercise at this point. Here's the strategy that we came up with in the first few minutes, and it's pretty obvious how it maps directly to our JavaScript below. So having this strategy worked out makes implementation really easy, but it also gives us potentially insightful comments that can make our code more readable. In particular, it would be pretty nice to include this part, which explains the broader conceptual purpose of the condition at line 19. So I'll add that as a comment right here. Now, if you're not using JavaScript, you may be concerned that we could access invalid or incorrect indices at lines 16 and 17. If that's the case, you can just check that the indices are valid before accessing them. But in JavaScript, it doesn't matter, so I left that out just to keep things simple. This was a long drawn out process because I wanted to show you everything that's happening in my mind when I see something like this. But if you watched me do this in real time, it would be really fast, maybe about 2 or 3 minutes from beginning to end. And the reason it would be like that is because we get the answer for free just by reading the question carefully. Just by ignoring the things that don't matter and rephrasing it slightly, we get the answer right away. It will take some time to consider whether it's correct, but this was also pretty straightforward, given that the way we conceptualized the problem was so close to the problem statement itself. So that really wasn't a difficult issue. And since the problem is so simple, I wouldn't really take the time to draw this out in real life, but this is a picture that I would see in my head before implementing. And then finally, an important piece is that if you get the simple approach first, and it's obviously correct, and you've done all the checks, you won't be as tempted by something like this. But if you don't get the simple approach first, you will find this very, very tempting. When you only have one answer, that thing becomes very, very attractive. So it's important that when you get free answers just by rephrasing things, you take those opportunities, and you do that by carefully analyzing the problems, rephrasing it, thinking about correctness, and so on. Now, if you do happen to become tempted by this idea, it's important to think about correctness right away so that you can notice the double counting issue that we found out, and then you can decide if you want to figure out a way to fix it or try to find a simpler approach, which was our original one. But maybe you didn't know that one right away, so it might take you some time to get there. And then the last point I'll say is the implementation is the least interesting, most boring part, and it's important to do everything you can to delay that until you fully understand the problem. If you do it that way, when you come to implementation, it will more or less be a typing exercise, and that's how it should be. The process I've taken you through is very similar to the experience that we have for our students at Watch and Code. Now, a lot of this you can do on your own, but at some points it can be really useful to have the assistance of a skilled instructor. The first place is when you're solving the problem on your own, you want to keep it that way as much as you can. But if you do get stuck, you want to get the smallest hint humanly possible. And that's where a really skilled instructor can help. They'll get into your heads, figure out exactly where the blind spot is, and slightly nudge you in the right direction, and then send you back on your own. Another important point is when you think you're done and you submit your work, you want to get really high quality feedback that addresses the strengths and weaknesses of what you did. And if you're not quite there, you want to keep working on it until you reach a high bar. And so that's another place where it can be really useful for someone to assess your work, give you feedback on it, and help you iterate on it. The last important thing is you want to reflect on what you did versus the ideal approach. And that's kind of what I'm trying to show you in this video. The biggest growth opportunities will come from slowly closing these gaps over time. So wherever there are gaps between your approach and the ideal approach, you want to try to close them. And here again, it can be really useful to get very targeted feedback on how you might make those changes.